Which of these three domino lines will fall the fastest? Pause the video here if you want to have a think about it. Actually, there's two different ways we could define fastest. Each line has the same number of dominoes. We could look at which line of dominoes finishes first. That tells us which is the fastest in dominoes per second. The orange line is the winner. Or we could look at when the falling dominoes pass the finish line. That gives us distance per second or velocity. The orange line is also the winner here, even though it has to knock down more dominoes for a given distance. Why is that? Let's look at the physics. This is a side view of a domino, with the centre of mass in the middle. We need to give enough of a push to get the centre of mass past the pivot point, and after that the torque from gravity continues to accelerate it all the way down. If we look at the horizontal component of the domino velocity, it increases until almost 50 degrees off vertical. So if we're going for the maximum average velocity, you might think that we should space the dominoes pretty far apart, so that they have time to accelerate to a decent velocity, and so that they give the next domino a good thwack. So far we're only considering one domino at a time though. Look closely at what happens when we knock down a line of dominoes. They stack together. The leading domino is not free falling, it's being pushed by a number of preceding dominoes that are leaning on it. That force produces a torque that is much stronger than the direct effect of gravity on that domino. That's because the weight here is pointed almost straight through the pivot, so it doesn't produce much torque. When I first started making this video, my hypothesis was that more closely spaced dominoes would result in higher torque, and that's why they fall faster. But that's not actually the case. If anything, the torque is a little higher with wider spacing. So let's dig deeper again. If you listen to the sound of dominoes falling, you can hear that the toppling starts very slowly when there's not many dominoes in the falling train. Then it speeds up as the dominoes stack up, until a maximum velocity is reached. And the line falls at essentially constant velocity after that. Why is there a terminal velocity and how do we work it out? The easiest way to think about it is in terms of energy. Each domino has some gravitational potential energy depending on the height of its centre of mass. As the dominoes fall, the liberated potential energy, represented by the blue bars, turns into kinetic energy in the system, the motion of the dominoes, represented by the red bars. Now it's not as simple as domino 1's potential energy going into domino 1's kinetic energy. In fact, here the leading domino has gained some potential energy to get over its pivot point, but it's also gained kinetic energy from the other dominoes. That's where the force we showed before comes in. It does work to transfer energy between dominoes. The dominoes keep accelerating in this way until the leading domino collides with the next domino, and in this collision we have some energy loss. By that I mean that some of the kinetic energy turns into heat and sound, and then the falling phase repeats again. If we look at a graph of kinetic energy, it's a sawtooth shape. We have alternating acceleration, collision, acceleration, collision, acceleration, collision, like a teenager driving a dodgem car or a bumper car. If the kinetic energy gained during each acceleration is the same as the kinetic energy lost during each collision, like it is at the end here, then we've reached terminal velocity. We can see the same thing if we plot the velocity of the leading domino. Then from this graph we can work out the average velocity. This graph is actually angular velocity, but we can then calculate the linear velocity from that. Let's repeat this for different spacings. What do we find? We find that wider spacing increases the average velocity during the fall, both angular velocity and linear velocity. So what on earth is going on in the video I showed you at the start? Why is the closely spaced line the fastest? That's the opposite of the graph I just showed. Well, actually the answer is simple and perhaps a bit disappointing when you hear it. For the closely spaced line, almost half the distance consists of the dominoes themselves. As soon as a domino gets hit on one side, the other side of it starts moving almost instantly. Technically, the shockwave propagates at the speed of sound, which is over 2 km per second in plastic. Any distance we fill with plastic is less distance that the much slower falling wave has to cover. So if we calculate velocity only over the space between dominoes, that velocity increases with spacing. But normally we calculate velocity over the whole physical distance. That velocity decreases with spacing. I wanted to cover one more thing that significantly affects the terminal velocity: friction. There's friction with the floor and friction between dominoes. The friction with the floor really just needs to be high enough for the dominoes not to slide. If the dominoes slide on the floor, the behavior can be complex, but ultimately some energy is dissipated, which reduces the velocity of the domino line. On my wooden floor there's a tiny bit of sliding during the collisions, but generally this is not a significant factor in the velocity. You might be surprised though, friction between dominoes makes a huge difference. Here's a plot of terminal velocity versus the amount of friction between dominoes in simulation. Why is this? Well, if we look back at how dominoes fall, we can see that each domino is constantly sliding on the next one. If there's a lot of friction between dominoes, then that's a significant source of energy loss. So to summarize, if we want the fastest domino line, We need low friction between dominoes and close spacing. And the reason for close spacing is really just to fill more of the distance with plastic. But it was fun to learn about the physics of dominoes falling. As usual, there's a lot more detail in my blog post that's linked in the description. Free body diagrams, equations, simulation code, and so forth. Do please like and subscribe if you found this interesting.